Hey guys, welcome to the follow-up video on the Tektronix 454A I picked up recently. Towards the end of the video I mentioned a couple things. One, that I was going to get some replacement feet. They have arrived. Some of them are 3D printed. We want to check out the quality, see how they fit, see how they work. And two, to compare it to a digital scope. So this is a scope you've seen me use in many videos. It's a Hewlett-Packard 54600B from the early 90s. So it's not a state-of-the-art digital scope by any means, and it's got some analog type features like some analog TV specific features. But it is a digital sampling oscilloscope. This is pure analog. Dual channel 150 megahertz, dual channel 100 megahertz. What I want to show you is, hopefully, some instances where this will give you a better look at the signal, but I want to show you why you might want to choose a scope like this instead. So I've seen a number of you post that either you have scopes and aren't sure how to use them, or you're thinking you're getting a scope and you're not sure how to use it. I'm not going to do an oscilloscope tutorial because I'm not an expert by any means. Part of that is because this is the scope I'm used to using. It's the scope I used in college. It's the scope I've used in a lot of my videos and projects. And the key to that is this magic button. First, let's talk about feet. When I got this scope, 3 out of the 4 bottom feet were gone. And all of the back feet were damaged. One so bad it was just completely broken off. The replacement bottom feet I got might be real Tektronix replacements. I'm not sure. They are molded, cast, I believe, and they look exactly like the originals. So all I need to do is loosen up this knob on either side, pop the bottom off, and put those 4 feet on. Great. The back feet, well, so these are 3D printed, and the seller sells a number of reproduction Tektronix parts. I kind of wish he'd make it more upfront that they're 3D printed, because on some of his listings it's kind of buried towards the bottom that they're 3D printed. I know a lot of you are proponents of 3D printing or have encouraged me to give it a try. We'll see. I'm dubious as to how long these will hold up. The originals had solid metal parts going down the middle with hard rubber on the outside, and they screwed into the back. The new ones have no metal. It's just a 3D printed piece of hard plastic, and you're going to screw down the middle and pop it on. I've already installed 2 of them. And so they don't have this wide metal base at the bottom like the originals did. So I got to imagine that this original with the metal collar arrangement is going to be stronger than this. I mean, I have no doubt if I went like this, this would crack off. So we'll see. The one that was completely broken off, that one, the screw that or the threaded part that it would go into is gone. So I can only attach 3 out of the 4. I figure that's better than nothing. At least it would be somewhat stable. For this one, maybe I can glue one on. Something like that to what is left there. Or maybe drill and tap a new hole that's a little off center. Won't be as strong as the original, but it would be something. Because the scope, well, normally when you use it, it's going to be resting on this handle and the 2 back feet. But when you're carrying it, storing it, it's often handy to put this in the vertical position. You can rotate this handle so it's going this way. And you can wrap the cord also around those feet. That's why they have these indentations for wrapping the cord around. Alright, so I'll pop these feet on and then let's get to actually using it. I installed the feet on the bottom. I could not be happier with. Perfect fit, perfect rubber hardness, exactly like the originals were, I imagine. The back, well, time will tell. I am a little puzzled as to why didn't they print this so that you could slide the metal collar down. Unless they're thinking, well, maybe you don't have that piece. in which case this is an all-in-one solution for you. Well, I do need to install the back before I can really properly install these, and I need to pound that flat. So we'll take another look at that in a bit. For now, let's check out what this scope can do for us. So what I want to look at is something I don't think I see too often on other YouTube channels, including my own, is the IF. I imagine many of you have seen what an audio waveform looks like on a scope. Jumble of sine waves corresponding to the sound that you're hearing. Or the local oscillator, I showed that earlier in this series, which is just a nice clean sine wave. Well, the IF is going to be, in this particular radio, a 175 kilohertz sine wave modulated with whatever we're receiving. So I hooked up my scope to the plate of the IF tube. I could probably also go to the grid of the detector rectifier tube, but in this case I chose to go with the plate, and it's grounded to the chassis. So that's what that's hooked up to there. Now, the fun with analog scopes is you get to play around with the controls and try to see something. Alright, so I intentionally put this on ground because I wanted to start out with nothing. So we're going to play around here. One, we got AC or DC coupling. DC coupling means it's going to include the DC component. Now I got this on the plate, which is going to be a couple hundred volts. And I particularly want to feed that into my scope. I just want to see the AC. So that's like putting a capacitor in series with the probe. We're blocking the DC. We're just seeing the variations in voltage. Alright, cool. We've got something. It's totally off the screen. So for that, we've got volts per division. That controls how much the scope is amplifying or attenuating the input signal. It's way too high, it's off the screen, so we want to go counterclockwise. Cool, we've got something, and it's doing something. I'll turn the volume up on the radio. So yeah, the sine wave is going up and down along with the sound we're hearing. Cool. Now I get a better look at it. So let's expand this out a little. So the final control is time. How much slice of time are we seeing across the screen? So that is a 175 kilohertz sine wave, and the crazy variations are the station we're receiving, the modulation. So if I go back the other way, we should be able to see the modulation better and better. Well, that's exactly what I was hoping to see. Now, say they were to play just a clear tone on this radio station, we would see this modulated with a sine wave that we could lock onto, and it wouldn't be so jumbled. But because the modulation is constantly varying as they speak, the scope can't lock onto it. What do I mean by lock? There's something called triggering. That determines when does the scope start sweeping from left to right. And you can control that with this level control here. And that, when that light is on, it means they've locked onto something. You see how it's flickering? It's because I've adjusted the control so that I'm only locking when the signal hits a certain amplitude level. If I go too far, it's just not going to lock at all. Because I'm telling it to lock on a signal that's like up here, and it never gets up there, so it never locks on anything. So it just it starts free running. It's just kind of, it's just sweeping from left to right continuously. Asynchronously, I guess you could say. But that's what I wanted to show, is that you can see the actual modulation in action. So with the lower setting, where it's taking more time to go left to right, we can see the audio signal. We go to the right, we get faster and faster sweep. Now we're seeing the intermediate frequency. So that's really nice. Now, let's see what it looks like in a digital scope. Okay, now the digital scope. A few differences right away. It's not as deep. It also weighs considerably less. Tektronix, 25 pounds maybe. This is like 5 pounds. So it takes up less space, weighs a lot less. Both kind of noisy, both have cooling fans. And this has to boot up. It's got an operating system of sorts. And what do we get? We got nothing. Notice there are less controls on this. Well, that's when I mentioned that magic button. So if you don't know anything about scopes, take this probe, hook it up to something, just push this button and the scope will do its best to give you something stable to look at. So let's push that button. And hey, there we go. There is what I presume is the carrier modulated by the audio. But if you look closely, it's not quite as nice looking. Now it's kind of jagged here and there. That's the sampling. So whereas the analog, it's just displaying whatever goes through the amplifiers from the real world. This is taking a little snapshot every, whatever, 10 nanoseconds, 100 nanoseconds, something like that, and digitizing it to individual points. Downside is modulation generally is not as nice to look at. But the carrier looks alright, and we can manually override the auto scale settings. So this is the voltage. Notice it just shot off the screen, and now we've got nothing. So all I did was turn one control once and I have nothing. Now we go back to the auto scale. So what did I screw up? This defaulted to DC coupling for some reason. I want to do AC coupling, and now I've got nothing. Well, it's because it's built in an offset because of that DC voltage. Mine has 250 volts, so I have to turn this position knob to get it all the way back up onto the screen. Now, since I'm familiar with the scope, I could have started manipulating these controls instead of hitting auto scale. I just wanted to show you that generally hitting auto scale will give you what you want without having to mess around with anything. So now I can change my volts. Here, relay clicking inside. That's switching in and out to attenuator positions. It's like a rotary switch, but I'm doing a digital knob and it's controlling a relay inside to change the voltage divider. And then this little knob over here is the time base. So, as before, we can go higher. Now we're just looking at the carrier, and if we start going the other way, we'll start seeing the modulation. But here's the difference I wanted to show you. That's not so nice to look at, is it? It's really hard to see the audio modulation very nicely. It's just a bunch of sharp spikes. There are some controls that can maybe sometimes help, like bandwidth limiting, but no, not really. So depending on what you want to look at, digital versus analog scopes with similar bandwidth. I gotta say the Tektronix, if you want to look at an AM modulated signal, wins hands down. This is just a mess. If you just wanted to look at the carrier though, I'd say they're about dead even. Yeah, it has a little bit of sampling noise on it. But yeah, other than that, the pros of this being it's small, lightweight, it's got the auto scale. And if you put this in 2-channel mode, it does not do the alternating back and forth. It does both simultaneously, which is another big advantage depending on what you want to do. For example, if I got a second probe, I could look at the local oscillator at the same time I'm looking at this signal. I'm sorry, I don't have a second probe handy right now, but imagine there's a sine wave down here locked to the same synchronization. Value-wise, if you were to go shopping for these, I have a Tektronix 465, which is similar to the 454, but it has less bandwidth. It's 100 megahertz dual channel. I think it's a little bit newer. So very similar specs to this scope. This scope I got for $100. Somebody had a number of them. They got it some liquidation from a lab or something like that. That was 10 years ago. They should be even cheaper now, I would think. Tektronix 465 that's been refurbished working is going to cost about the same. Maybe a little more. because it takes a little bit more effort to find one in good shape and get it all working properly. On the other hand, if anything inside this breaks, I have very little hope of being able to fix it. The 454, yeah, I could possibly replace a transistor, a resistor, a capacitor. They're hand-selected components for a lot of the transistors, for example, but they are off-the-shelf parts. All right, so there you have it. Pick your poison. So how would a brand new state-of-the-art digital scope works? Well, let's not go crazy. I mean, we're not talking about a $100,000 digital scope, but like a modestly priced scope for $400 or $500. You know, I don't know, because I've never used one. I just know what I've seen on YouTube, and I know they have greater bandwidth than this scope, and they have faster sampling rates. But what they also, I don't think have, or they don't, I think the one downside, is that they can't handle as high a voltage. So right now I'm looking at a signal that's got a 250 volt DC offset to it. I don't know that some of those little pocket digital scopes could handle something like that. So that's something else to keep in mind. I'm not sure exactly what this scope can handle, but the Tektronix I know can handle hundreds of volts. And of course the probe divides it down too, so that gives you some extra headroom there too. So let's see. This goes up to 50 volts per division. So top to bottom, you could do 400 volts. I don't know what the actual max is on the input of the scope, so you wouldn't damage anything, but you can display 400 volts. I don't think most modern, inexpensive, all-digital scopes can do 50 volts per division. They might top out at 10 or something like that. I could be wrong, but I think that's generally how it goes. In other words, you're going to have a harder time breaking an old scope by attaching it to something wrong. Hang on, before we leave the digital scope, there are some other features that can be invaluable that I should mention. So let's auto-scale this again. So we're looking at our carrier, right? It might be really nice to know what frequency that is, or what the peak-to-peak voltage is. This one on the analog scope, you'd have to look at your time-based control and see how many divisions it is between two peaks and find the period, and then do some math to find the frequency. And to find the voltage, you'd have to count up your vertical divisions and look at your voltage per division setting on your input control. On this, well, we've got some buttons we can push. So time, and we want to see frequency. Because it's modulated, it's having a little bit of trouble, but there's something called cursors we can push. And then we can tell it we want to measure from this point. And then do T2, we want to measure from the first point to the second point. And it tells us the frequency down here. It's not perfect. And I don't know that I have it perfectly lined up on the peaks, but it's about 175 kilohertz. And we can do similar for voltage. We can do peak to peak, which of course is going to vary, but we can see it's around 18-20 volts peak to peak. That's really handy to be able to do at times as well. Newer scopes can do more. They probably do Fourier transformations and all kinds of nifty things that require a lot of calculations. Just something else to keep in mind, because if you've got this, you can kind of get away without having a frequency counter, which is one reason why you rarely see me use one. Here's a look at the back. I hammered it flat, installed 3 out of the 4 feet. Here's the one that was damaged, where I installed a replacement potentiometer. I need to still find one that's the correct size and mount it more securely, and then figure out what to do to secure another foot here. I could perhaps drill and tap a hole so I can put a threaded, screw into it. Or I could maybe build up that broken off piece with some JB weld and put the screw into that. But for now, it'll do. I can balance it on the 3 feet, kinda. And I do need to replace the line cord. I took this little door off and it's a bit more involved than I expected, but eventually I will get around to it. Here the two are side by side. You can see now that this also has a much larger screen on it. Now, of course, there are many other oscilloscope models that have a wide range of features. This is just what I know. This is what I have the most experience with, which would be early 70s Tektronix and early 90s Hewlett-Packard. I like them both. I use them both. Depends what I want to do. If I want to look at certain types of analog waveforms, this works better. I didn't have a chance to show it to you, but maybe in an upcoming project when I do a TV, this generally is also better for looking at an NTSC type video signal. You've got both AM and FM modulation. You want something quick and easy to use. Maybe you're not looking at such complex waveforms. This is a great option as well. Hope you enjoyed this look and comparison between a digital and analog oscilloscope.